Hi, chemistry. This is a follow-up to some work we've already done, specifically the electronegativity work looking at bond types. So there's a little bit of a review of the different types of bonds, and then has been our kind of pattern all along, we'll take the fundamental definitions and we'll start to look at the consequences of those in substances. And in this, we're going to look specifically at the expression of bonds through physical properties. So a little bit of terminology. This came up, I think, in one question when I was doing one of the coffee and chemicals demonstrations about forces between particles. So there's a little bit of terminology that we need to get here, and that is intra versus inter. And this is terminology that's used in computer networking. The computer network within the building that connects your computer to the Wi-Fi is called an intranet. It is within the building. So I need to set my pen color here real quick. So intra means within, and inter means between. So the internet is the network that connects one building to the next. So in this example of hydrochloric acid here, there is an intra particle force that holds the hydrogen and the chlorine atoms together. But this is a covalent bond. It's actually a polar covalent bond. And so what happens is the chlorine ends up being the delta negative and the hydrogen ends up being the delta positive. So when another chlorine or another hydrogen chloride, another hydrochloric acid approaches it, we have the same polarity, and you can see how we get opposites attracting. So this is a force that happens from one molecule of HCl to the other molecule of HCl. So this is what we'd call an intermolecular and interparticle attraction. So the internal bonding, the intraparticle bonds, really define the substance. They define its reactivity, whereas the intermolecular forces, those are going to mostly define the physical behavior. So we kind of sum that up here, that intraparticle forces tend to have the greatest effect on physical behavior, such as state, so solid, liquid, gas, viscosity, how fluid is a particular liquid or a gas, or even solids can actually behave as a fluid. If you take something that's solid and you bend it, that technically is a fluid behavior. Density, two elements occur at different densities because not only are their atoms different masses, but the way the atoms interact with each other is different, so that affects their spacing. And then whether or not a substance will dissolve can be affected not only by the intraparticle forces, but also the interparticle forces. And I just realized here, my little slideshow has a typo in it. Interparticle forces. So those are the forces from one particle to another. The intraparticle forces tend to have the greatest effect on chemical behavior, so reactivity. If you're going to pull the atoms apart and rearrange them into something else, then the ability to pull them apart, or the motivation to pull them apart in terms of energy and entropy and enthalpy and all of that, is based on the types of bonds that are there in the first place. However, we have to remember those two things do not exist in isolation. And we look back here at how the nature of this intraparticle bond between hydrogen and chlorine produced the ability for the intermolecular force to occur due to the polarity of that particular molecule. So they are definitely connected to each other. And so if you kind of know what type of bond a substance has, or you know the nature of its internal bonding, you can make some predictions about, or at least some explanations about why a substance has a particular behavior. So just to review ionic bonding. Ionic bonding is when we have a large difference in valence behavior, often elements of opposite ends of the periodic table, large difference in electronegativity, and this forms an ionic compound. So in the case of sodium and chlorine, the electron gets transferred and you end up with actual separate ions that just stick to each other. It really is kind of like a static cling. And this occurs in all directions. So if we visualize the green here as these are your chlorines and these are your sodiums, you really can't, directly identify which sodium goes with which chlorine. There's this network, this framework of alternating sodium and chlorine ions that produces the material. And if we get a chance, we'll look at table salt under a microscope. And if you look at table salt under a microscope, it's always little cubes. And those little cubes represent the three-dimensional connecting of the sodium and the chlorine atoms. So because you can't specifically identify any pairings in here, we can't call it a molecule. A molecule has to be a definitive collection of atoms covalently bonded together. So we would use the term formula unit when we describe NaCl. We can't say a molecule of NaCl, we say formula unit of it. So the consequences of this are that, it's not too hard to pull these ions apart if you have a polar molecule where you can attract the chlorine to a positive pole and you can attract the sodium to a negative pole. It can be pulled apart, and that's the process that happens when you dissolve salt in water. But because all of these sodiums and chlorines are all linked together in 3 dimensions, that means it's very easy for sodium chloride to hold a structure. And that would explain why salt is a solid at room temperature, is because it has a very good ability for the different particles to lock themselves into a particular shape. Covalent bonding is when our behavior is more similar. And so you can have purely covalent bonds. And really the non-polar covalent bonds show up most often in the diatomics. So diatomics are elements that under natural conditions tend to form these little 2 molecules. You're probably familiar with oxygen being O2 in the atmosphere, but all of these elements as an atmospheric gas will form little molecules under the buddy system. So I kind of remember them by the mnemonic Hanaf-Brickel. But there you have 2 atoms of exactly equal electronegativity. So that is going to be a purely nonpolar covalent bond. Almost all other covalent bonds have some degree of polarity, and that degree of polarity producing poles can then influence interparticle attractions. Now, it depends a lot on 3-dimensional situations. So like when you have your hydrogen oxygen down here, with oxygen being the delta negative, hydrogen being the delta positive, opposite ends of the molecule, and you can see how that can become, like a magnet and attract things. But there's another molecule, sulfur hexafluoride, and so hex means 6. And so fluorine, being the most electronegative of all of the elements, is going to kind of create this delta negative shell around the outside, and the delta positive sulfur ends up being buried way down in the middle. So if you get in your magic school bus and you drive up to the outside of a sulfur hexafluoride molecule, even though this is extremely polar bonding, from the outside, you can't see the positive pole. It's buried down within the center of the molecule. So just because something's polar doesn't mean it's going to be the same. We look at water, and water is a fairly polar molecule. And that allows water to stay together as a liquid at room temperature because the poles are exposed and it's a fairly strong polarity. But sulfur hexafluoride, where the poles are not exposed, sulfur hexafluoride, even though it is more polar than water, sulfur hexafluoride is a gas at room temperature because the polarity that exists is not laid out in such a way that it can greatly influence the properties. As a matter of fact, the outside of the molecule is so negative that the molecules tend to repel each other, and that's kind of the definition of a gas, is something where the molecules are not attracted together at all. So we have metallic bonding too that I want to mention. This is kind of a definition to throw out. The thing with metallic bonding is pretty much we let those electrons freely move, and this fact that the electrons can kind of freely move is what produces the metallic properties, able to conduct electricity, able to be bent, that the atoms can move relative to each other. And if the atoms can kind of move relative to each other and affect each other, that means the vibration of one atom can be transferred through all the other atoms, which is why metals tend to transfer heat. So it's just a different type. It's sometimes referred to as a sea of electrons in metallic bonding, so that you really can't associate those valence electrons with any one atom. They're just kind of moving throughout all the time. So to summarize these consequences, whoa, don't know what happened to the spacing there, but ionic bonding, high melting points. In other words, they have a greater tendency to be solids at room temperature. And I say tendencies on all of these. It's just one of those things. If you're going to make a prediction, here's the prediction you'd make, but there's always exceptions, and there's other factors that come in that we're not talking about right now. But because ionic bond tends to be very strong in 3 dimensions, that holds the structure together into a solid shape. Because it is a static cling kind of situation, the ions can tend to be pulled apart by the polar water molecules, so they have a greater tendency to be solid or soluble. That the order of the ions, the shape, like sodium's cubic crystals, is a characteristic property of ionic compounds. But when you have just, I don't want this electron, you take it, there's not a whole lot of different combinations you can do with that, because sodium has an electron, chlorine wants one, here you go, and there's not much more you can do with that. So ionic compounds tend to be fairly simple, just one thing bonded to something else. Covalent compounds, though, because there's so many different ways that something can share, that's where you can really start to build very complex molecules, because carbon can share with oxygen, but then it could also share some with hydrogen at the same time, and they could kind of all share together, and then you can plug in some nitrogen and some other oxygen, and then the next thing you know, we have big complex organic molecules. So the complexity tends to be much more VSEPR, something we'll talk about later on, valence shell electron pair repulsion. It basically means that the electrons in those bonds tend to spread themselves around. So if you have something that forms 3 bonds, the bonds will spread themselves out around the nucleus, which ends up producing the shapes of a lot of covalent compounds. And that's part of why the water molecule is that V shape, because we have 2 unbonded electron pairs around oxygen and then 2 bonded pairs. That gives us 1, 2, 3, 4, 5, 6, 7, 8. And all those things spread themselves out around the water molecule, and that ends up producing that V shape. It'll be really important in the overall behavior of the water molecule. Covalent compounds tend not to be soluble unless they have some polarity to it. Sugar is a covalent compound, but it is soluble because it has so many hydrogen bonding sites. Hydrogen bonding is basically an interparticle attraction that specifically is due to hydrogen being a delta positive on some molecule. So hydrogen bonding is not a bond. It's just a common, important type of interparticle attraction. And because there's no specific structure, it's how much polarity, is there any polarity? There's sort of these weak links together. Covalent compounds tend to have a much lower melting point. So water is a liquid at room temperature, and oxygen is a gas at room temperature, because oxygen is completely nonpolar, and there's very little incentive for the water molecules to hook up with each other and become liquids or solids. There are some substances as well that can have more than one bond type, and we'll look at these. So in the case of ammonium chloride down here, the ammonium group with its 4 hydrogens, these are all covalently bonded together. So that's a strong little group there, NH4. So the hydrogens are very strongly connected to the nitrogen, but that group carries an overall positive charge. Nitrogen normally wants to form 3 bonds. In this case, it has 4. And so in order to kind of make this work, it gives up an electron. The chlorine, however, as we know, would be the one that wants to receive that electron. So while the nitrogen and hydrogens are all covalently bonded together, the ammonium group is ionically bonded to the chlorine. So when you put ammonium chloride in the water, it dissolves right there. The chlorine goes to attract to the delta positive end of the water molecule. The ammonium group goes to attract to the delta negative end of the water molecule. But the nitrogen and the hydrogens all stay together because they're much more strongly covalently bonded to each other. So intraparticle attraction, internal chemical bonding, that then helps produce the interparticle attractions, which create certain tendencies in terms of the behaviors of matter physically.